Hey guys, we're going to continue on with error correction in our lecture. We see here a long division problem, and CRC does to accomplish the separation that we talked about at the end of last lecture is basically pass the remainder along. That is the result of dividing your input string stretched out with some extra bits by a common divisor that we're going to call a generator, and that's represented by the letter G in this diagram. So what I'm going to walk you through is basically how this works, and we're going to go to a site that the author has set up, and then we're going to run through an example of it. Okay, so here is the sample site, and it's in the list of applications on our spreadsheet down here. This one, the last one on chapter 6. So that's the page that I'm on right now. Okay, so I'm going to generate another problem, and basically here's the way this is going to work. We are being given a 4-bit generator of 1001 and a data payload of 100110001. And I'm writing this somewhere else, which is why I'm reading it so slowly. I can read numbers faster, I promise. And then R equals 3. So here's the way we're going to do this. I'm going to switch over to a different app now. My new best friend, Sketchpad, Sketchbook, some best friend I am. And here I've written down the generator, 1001. I've written down D. All that's left to write down is R. And so here's what you do. You take the number, the data that you're being given, the number here, you multiply it by 2 to the R. 2 to the R, in our case, it's R is equal to 3, is going to be 3 zeros. And when you multiply a number in binary by 2's, you basically are adding zeros to the end. So like the binary for 2 is this. If you multiply by 2, you want 4. That's that. If you want 8, add another one, and so forth. And now I'm going to start dividing. And I'm going to use a very special type of arithmetic. It's modulo 2 binary arithmetic. And the weird thing about that arithmetic is addition and subtraction, first of all, are exactly the same, and you have no carries. So it's basically a bitwise exclusive OR. And the author gives you a link here, too much, right here, to a website that's a tool that's fantastic. So we're gonna use this here in a minute, but let's just ignore it for now because we're not ready for that. I'm gonna do some division. 100. What am I doing here? 1001 fits perfectly there, so that's a 0. I copy down the next number. That doesn't go. This one doesn't go. This one went one time, right? So I'll mark a 1 up here. Pulling this next one down here didn't do anything for me, so that represents a 0. Pulling this one down didn't do anything for me. That's a 0. And pulling the next one down didn't do anything for me, so that stays a 0 up here. But the next one, we're going to hit pay dirt. So when I pull this next one down, it's going to fit. 1001, it'll fit perfectly, in fact. I have a remainder of 0. What about the next 3 bits? They don't do anything for me. And so that's my answer. And what's my remainder? My remainder are these last 3 bits. So this is the number that I will transmit to protect this data. We both agree ahead of time on what the generator is going to be. So that doesn't get transmitted. That's built into the algorithm. So the idea here is if anything were to befall this string D, label it over here too. If anything were to befall that, the claim is that by changing 1 bit, 2 bit, 3 bit, 4 bits, you're going to have to do a lot to this to get it to divide by 1001 with still a remainder of 0. And let's think about it for a minute. What if I take a number that's 800 and I tell you I'm going to divide it by 2? The number's 400, right? So that's a small divisor, and it's going to give me 800 divided by 2 goes into 400 with the remainder of 0, right? Well, there's a bunch of other numbers that are going to give me a remainder of 0 if this is really what I'm interested in transmitting along with my data. What if I change this to a 400 or a 500 or a 550 or a 642? All of those also have a remainder of 0 if you divide them by 2. So this is a pretty bad divisor if I'm trying to ensure that stuff doesn't get edited very much and can still be detectable. Because after all I have to do to 800 to make it divisible by 2 is just change this digit. I can make it 810, still divisible by 2. So that's not a great way to go about sort of hiding stuff, protecting it. What I might want to do instead is take something like 800 and divide it by 646. Now, I have no idea what that's going to be, but we're going to take a look at it here a little bit. And that's going to get me 154 if I did this right. And so that'll go in one time up here, and there's nothing else, so that's my remainder. So what other numbers can I divide by 646 where the remainder is going to be 154 again? Well, you could give it 1600, but that's going to require adding digits, adding binary bits to your string. And if you have a fixed length packet, you're going to catch that right away. What if you subtract 154 from this, or add 154 to it? That's going to be 954, or whatever subtracting that gives you. Those are lots and lots of bit changes. So there's a lot more distance between this and this, which is the next adjacent valid number. And so all the things I could do to this number in between, like 810, like I did a minute ago, or 802, none of those are going to come up with the same remainder. So I've inserted a bunch of space between one valid number and the next. And in the other direction as well, it would be 646, something like that. I don't know. Maybe that's right. Maybe it's not. 464. So 646. So anyway, you're creating some space. So let's go back and let's see if I'm right, because half the time I'm not. So we'll stop sharing both of those, and I'm going to come back over to just sharing Firefox and go back over to my interactive site, and let's see what the solution is. The solution is 0, which is what I had guessed here. The other site can give this to us as well. So what I'm going to need to do is unhide the number that I gave you guys a minute ago, and we're going to type it into this site. So I kind of have it peeking out the side. You guys can't see it, but I can. So what this one was 1001100100 divided by 1001. So I select divide. I make sure all three of these are turned on. Usually polynomials isn't, and I hit compute. And what I'm going to get is remainder of 0, and it sort of walks you through the way this thing worked. So what I'm going to transmit is, as my check, is 0. It's called polynomial because you'll notice if you want to figure out what the divisor and the quotient are here, you can represent it as binary, or you can represent things as polynomials. So 1001, if I put this up here and divide those two from each other, 1001 has a 1 in the 2 to the 0th position, and it has a 1 in the 2 to the 3rd position, which is the same thing as saying 1, and let's use x cubed. If I had 1101, that's going to be x cubed and x squared in 1, because there's now a 1 in the x over 2 position. So these exponents represent the power of 2 slot where the 1 is. and all you're really doing is dividing polynomials by each other. All right, so that's weird, but that's why it's called polynomial calculations. Okay, off on the side. What I've left you in here is a little bit more data on how things work, and we're going to fly through and glance at a few of these things. And what I'm showing you here is from the University of Washington, and the credits in there for the author. Thank you. There's a signal that I'm trying to encode, and it's shown in blue. So I'll stick with blue, and we're going to show how you would encode the binary string 0110001. So here's 0, 1, whoops, I can't let go of my mouse, 0, 1, 1, then back down to the low part of the signal, 0, 0, 0, 1. So what am I doing? I'm showing you a possible sine wave pattern that I would want to pass through a digital to analog converter to get it onto copper, let's say, that when received at the other end would be interpreted as 0, 1, 1, 0, 0, 1. Now this depends on the fact that I chose 0 to be this voltage and 1 to be this voltage, and I have a certain frequency range. And having a bunch of zeros together doesn't bother me at all. So if I introduce a little bit of noise into this, we should still be able to get the answer out. But a very noisy line, might corrupt it, right? So a very noisy line slightly might look like, and a very noisy line might look something like that. So we're going to have a problem figuring out, well, was this supposed to be a 0 or 1? So you'll put some space in between the high level and the low level, and you'll usually ignore things around the center point. You're going to create what are called guard bands here. So nothing below this or above this will be considered valid. And that gives you some room where this signal can be perturbed by running into noise, and it can be amplified or attenuated, and you'll still be able to tell it's a 1 versus a 0. So one of the things you can do is add check bits, and then I'll tell you what I'm noticing is some of the graphs didn't come out right when it just got picked up by PowerPoint. So when I'm done with this lecture, I'll take these slides out of slide 18, and I'll put them in a separate something that says slide 18 supplement 1 slides for lecture 18 supplement 2 right there along with it in the slides folder, but I'll put them there so they look okay. All right. So Hamming was scary smart, and what he came up with was a way of putting distance between valid strings of numbers. So it's similar to what we've been talking about. And so what I'm going to show you is the basics of how to do Hamming code. So this is another take at valid code words in blue, and all the other ones are possible bit combinations. They're valid bit combinations. In regular binary, they're perfectly good numbers, but in our scheme, we sort of multiplied numbers by something to spread them out. And so if your bit errors that you experience in your technology happen to move these things sort of one square over at a time, then you're somewhat immune from errors, and it's going to take an unusually big error to cause you to have some heartburn here. So single bit error from A, it takes 3 bit errors to get to B, right? So that's basically what we're saying. Okay, so I'm going to switch presentations and show you some Hamming code slides. And why do I have 2 copies of this chapter? We don't need 2 copies of this. No, I do not. And there's 2 documents I'm going to reference for you, and then we're going to walk through kind of a live design. There's an excellent textbook on computer organization design by Patterson and Hennessy. There's a chapter on Hamming codes I put out there if you're interested. There's also one on error detection and correction that came out of a textbook called Logic and Computer Fundamentals. This one's much shorter. It actually walks you through a few things and some exercises. That's out there if you want. The thing I wanted to show you, though, to walk you through this is right after these slides. And if you guys have seen Hamming codes before, bear with me for 5 minutes. So the idea behind Hamming codes is we're going to intersperse some parity bits, and we're going to do it in the places where there is only a single digit to represent, only a single 1 required to represent a particular binary number. And that's going to turn out to be all the powers of 2. So if I notice these patterns here, and I basically say this is a 1, a 2, a 4, and an 8. 3 is going to be represented like this because it takes 2 plus 1 to do that. 5 will be a 4 and a 1. 6 will look like this. 7 will look like this. Here's 8. 1, 0, 0, 0. Pretend the x's are 1s. And then 9 would be this. 10 will be this. 11 and 12. And the reason why I'm going to stop at 12 is because I don't have very much to send. So with these reserved and out of the way, because they only have one X in that column, all the other ones have more than one X. And we're going to make these columns reserved for where we're going to insert the parity bits. So our data bits, we have 8 of them. We've been given 1 byte. That's D1 through 8. So the task basically is to now show a formula for what are we going to put in these, in this case, 4 parity bit fields that we've got. We're not going to need many. We only have 4 bits. But how are we going to calculate what goes in there? You're going to do parity just like we learned before. So if the number that I'm asking you to transmit is 1, 0, 1, 0, 1, 1, 0, 1, then what you're going to do is start filling these things in. So 3, I erased the x's, I remember where they were. And because there was an x here and there was an x here, I'm going to copy this number from my data and write it in to these 2 squares, right? Because that's where I had the x's. Do you remember what came after 4? It was 5, right? It was here and here. So I'm going to copy my zeros down here. 6 was here and here. 7, which is a 0 up here, so I'm going to copy the 0 down to these. Every place where I had x's. Now the other tools I've made, I left faint x's in here, but I threw this slide in and didn't put the faint x's in this time, so it's kind of on me. So 8, 9, 10 is an 8 and a 2. There's zeros for data 7 bits, so where am I going to put the zeros? I'm going to put it in position 8, 9, 10, 11. So 11 is an 8 plus a 2 plus a 1. And then the last one is going to be 12, which is going to be 8 and one of these. All right. Starting with the first row, how many 1s are there? I count 1 here, and I count 1 here. That's even, so that's a 0. What about this row? I count 1 here, here, and here. That's odd, so I need to make it a 1 to make it even parity. The next one has 2 1s, so that's a 0. And the next one has 1, 2, 3 1s, so that's a 1. So now I know the value that P1 should have, and so I can fill it in down here. And the next one is P2, and I know what value it should have now. It should have a 1. So I'm going to fill that in. The data, I don't change. I'm trying to protect the data, not obliterate it. P4 is a 0. 5 is a 0, 1, 0. 8 was a 1. P8 was a 1, and the rest of these I fill in. This is the string I transmit. It's 12 bits, so it's 50% bigger than the byte. But if you send more bytes, powers of 2 get further apart, and you don't have to send as many. So the idea is at the other end, I can take my data that I've got, and it'll basically 0, 1, 1, 0. 0, 1, 0, 1, all right. 0, 1, 0, 1, and 1, 1, 0, 1. 1, 1, 0, 1. So I'm going to fill the things back in. Thank goodness this time I remembered the faint x's. Boy, it goes a lot faster. And then I'll put 1s in here. Whoops. I'm just copying the number from above into every x'd square. Okay. Now, if I calculate the parity now, it should all be zeros, because if I needed a 1, I inserted a 1. That's what I set the parity bit to. So this row has 4 1s now. The parity bit made it even. What about in this one? Same thing. The parity bit here, where is the parity bit? Parity bit here was a 0 because there were already 2 1s in this row. So if I recalculate the parity across all these numbers now, it has 2 1s. That would be a 0. And what if I calculate the parity brand new from this? 1, 1, 1, 1. That's 4 zeros. All of these came out zeros. that means there's no errors. That's what that means. All right, so let's back up now and intentionally include an error. And I'm going to get rid of a couple of things here. And we're going to recalculate stuff. So I'm going to switch to a red pin. And let's just pick a bit. Let's pick bit 5. Let's corrupt bit 5 and make it a 0. So what that means is I would have copied a 0 down instead of a 1 into each of these. All right, let's try it. Let's go across this row and calculate parity. I see a single 1. That means this should have been a 1. I already know right now there's an error. So if that's all I need to know, I can throw the packet out. What about the next row? Nothing changed? Still even? Fine. This one's still even. And what about this one down here? This is odd. It should have been an even. You add these positions up, 1 plus 8, because they have 1 in them. You get 9. So that bit is an error. So what I'm saying is bit 1, 2, 3, 4, 5, 6, 7, 8, 9 is an error. And in fact, it is. So whatever I got transmitted, I received this string. And so I received, I think, a 0. I'm going to switch it to a 1 because that's what this told me to do because there was an error there. All right, so that's Hamming codes in a nutshell. All right, let's move on to multiple access protocols now. And what a multiple access link is a link that's shared among multiple people. And most of the time when we use Ethernet, we're no longer shared because we're isolated to just a switch. But Ethernet used to be a massively shared network, meaning there were tons of packets on it. And originally, you had this big, thick cable that everybody would connect to. And even in days after that, when we had kind of star configurations, the switch wasn't intelligent. So all it did was give you a place to plug your cables in that was inexpensive, but because that twisted pair, the Ethernet cable that we use these days, you know, the blue cable in this bag, is a whole lot less expensive than the big, giant, thick, stiff cable that we had before. So even if the only improvement was the cable, and I still saw everybody else's packets with this new device, that was okay. That was okay for a while. So old-fashioned Ethernet, there's some upstream high-speed communication channels. 802.11 Wi-Fi is absolutely a shared medium as well. So the problem with shared mediums is we want to be able to spot a collision. If 2 or more people simultaneously transmit an Ethernet frame, let's say, they can collide with each other. And it doesn't mean that they hit each other and bits go flying or a piece of the frame breaks off and, you know, with the license plate on it or anything like that. It simply means it's a combination of signals. And we're going to get a chance to divert from the book next week and take a look at more detail on exactly what that means. But for now, it simply means is if you have one sine wave, I'm going to overlay these on top of each other. If you have one sine wave that looks like this, and you have another sine wave that gets transmitted at the same time that looks like that, the combined signal is going to end up looking somewhere between the two. All I'm doing is adding these two things together and coming up with a new value. This one's going to go off the top of the screen and then back down again. So when these two things encounter each other on the wire, both of them can immediately see that this green line, which is now what they're hearing on the wire, doesn't look anything like the blue line the blue guy expected, nor does it look like the red line that the red transmitter emitted and expected. So they're going to transmit, and while they're transmitting, at this moment right here, the red guy is listening as he's sending this, and he expects to see this signal on the wire, just like a millimeter away from where he transmitted it. And instead, what he sees is this green thing. So he knows there's a collision, and the blue guy does too. So we're going to walk through how this actually works and how anything gets done when in this era of collisions. So the communication about the channel sharing, you know, must channel itself. It must separate users apart from each other. So we're going to create a protocol that sorts all this stuff out. And the ideal method is this. If you've got R bits per second that you can use, what you desire is that when when one node wants to transmit, let's call it node number 1, it can send at the full rate because it'll have the network all to itself. And then when M nodes want to transmit, each of them can get the whole network for a fraction of the time, but if you're fair about it, each of them will get the network 1/mth the time. So on average, they will have available to them, theoretically, R over M bandwidth. But the reason why this is better than fixing up a specific circuit that gives them exactly R over M all the time is because a lot of the times, the other M's next to you aren't using the network. And so you get to use it for longer. In other words, the probability of somebody using the network, let's say it's 10% and there's 5 users on this network, then most of the time it's empty. So if you come along and you need to send a big giant file, you've got it all to yourself for probably a decent amount of time. Maybe there's a collision here and you let get their little thing out of the way, but that's why we do this, is because we tend to act in bursts, and statistically we can get more done this way. Let me have the whole network, I'll get on there and I'll get off quick. All right, so there's no synchronization if we do it this way, and so we're going to show this in some detail. So there's 3 broad classes of these multiple access protocols. One of them is you divide things up into channels like time slots or frequencies. We looked at TDM and FDM. Another way of having multiple users share a network is to give people sort of random access to it. You allow collisions to happen. You just go up to a stoplight and you close your eyes and you just count to something. If you don't hear another car, you slam your foot down on the gas, and you just pray you don't hit someone. And if you listen and you don't hear anybody driving through the intersection already, there may be somebody else stopped doing the same thing, but that's really the only time you're going to have a collision. The rest of the time, if you zoom through when it sounds quiet, you're going to be okay, because as soon as you start making noise, nobody else is going to start. So it really takes this unusual simultaneous, at exactly the same moment, transmission before this thing's going to happen. So we're going to take a look at how that really unfolds on Ethernet. And then the third way of doing it is just taking turns, kind of a round robin. So here's an example of how to apply the TDMA time division scheme that we learned earlier in the semester, how you would apply it to this type of scheme. And in this case, we've divided our network up into little time bands that are further subdivided into 6 slots. And we're going to give each of 6 users one of these little time slots. So let's say this is a long enough amount of time to handle 600 bits. If you start transmitting from here and it was all yours, you'd be able to get 600 bits off. So what we're going to tell you instead is number 1 is going to get the first 100 bits. Number 2 needs to count 100 bits and then get the second 100 in and then be quiet. The third one needs to wait for 200 bits and then immediately add in 100 bits and so forth. So that's a way to do it. That's the way voice is transmitted over a telephone network, for example, because they use constant bandwidth, and you can fit 24 of them in 64,000 bits KB per second because there's 8,000 samples a second, blah, 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 blah. There's like lots of math around it, but it's all worked out like over 100 years ago at this point. So another way to do it is to channel partition. This might be where you do frequency bands. So this would be one person has this carrier, and so if they want to send a signal on it, they're going to perturb the signal to encode it with ones or zeros. So let's say if it's a 0, you go down, and if it's a 1, you go up. So some sort of perturbing signal, might change it like that. But it's not going to interfere with somebody who's using a completely different frequency, because their base frequency looks like this. Is it going to let me move it or not? Hello? Are you going to work today? Thank you. So glad you could come. All right. So you can perturb this one, and you're not going to make so much change to the green one that you can't do it. So you can separate things out by frequency that way. Random access protocols is where it's really interesting to us, because this is how radio and shared physical media work, and collisions can take place. So an example of one of these is a very, very famous one that was developed at the University of Hawaii. And the interesting thing about them is they had users who were sharing the same radio frequencies, and they would have radios that would transmit from each of the campuses on the islands that had them back to Honolulu, to the main University of Hawaii campus, and that's how they would then get out to the internet. I mean, can you imagine what it took to do that? You had to wait for somebody to lay an undersea cable for telephones and then use a few of those lines. So it was super limited bandwidth, but they further had to partition it among the islands. So the problem with the random access protocol there was the volcanoes blocked your ability to hear if the other person was transmitting. So even if you were trying to not conflict with the other sender, you had no way of hearing if they were sending something. The only thing you could hear for sure is what was coming back from Honolulu. Maybe you could hear a couple of the other campuses, but you might not hear one that you're competing with. So slotted Aloha was an incredible innovation. It came up with a scheme where all the frames are the same size, and you divided the time into equal size slots. Here, 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 here. You can send a frame here, 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 or here. Nodes start to transmit at the beginning of a slot. That's the only time they can do it. So there's got to be some sort of a heartbeat coming out from Honolulu, radio waves, and they travel at the speed of light. So even though there's some mileage between these islands, it's still close enough that the bits line up. They're not so far apart. So this synchronizes the nodes. And if two or more nodes transmit in the same slot, it's called a collision. And the idea is that all the other nodes would hear the collision because they'd hear invalid bit patterns, signal strengths that were too high or too close to zero or too low to fit the rule that they had. So they would know. It wouldn't matter why it was corrupted, they would just know that it was. So it could be somebody else was messing around with the radio on those frequencies, or it could be another campus was actually trying to use the radio. So when you are ready to send a frame, you get one up from above, from IP, and you transmit it. And you try to listen to see if there's a collision. If there isn't, you're good. If there is a collision, you're going to retransmit, but not necessarily in the next frame. You're going to use a probability of P to decide whether the next frame is the one when you transmit or not. So if it's a roll of the three-sided die, then a third of the time you'll transmit in the next frame, and a third of the time in the one after that, and a third of the time two after that. Why? Because the other person that collided needs to send two. So if you're lucky, you're going to roll different numbers, and the collision is gone, right? So you'll each have guaranteed to pick the different slot. Right, so here's how it works. Three nodes, they all collide, they all know it. This guy rolls a 2, this guy rolls a 2, this guy rolls a 1, 2, 3, 4, a 5. Okay, so the next round, nobody rolled 1, so this goes empty. This is an unused channel. That's inefficient, but that's okay. So we're going to throw away a lot of our radio slots here, but it's going to keep us from having to run cables between all these islands, save us money. And these two guys that rolled a 2, they're unlucky again. They're like, darn it, I can't win. But the next collision, this one here, 2 rolled a 1. So in time slot 3, he gets to go. Finally, one of the 3 has transmitted. Nobody rolled a 4, so that time slot's empty. 5, after waiting all that, 3 has a collision again with 1. This time he rolls a 2, he rolls a 3. Nobody uses this one. 1 goes, 3 goes. So it took us 5, 6, 7, 8 slots to get 3 packets out. That's about 1/3 efficiency. And in fact, it is what the efficiency works out to. And the way you calculate whether you're going to be successful is you figure out the probability that you're going to have success that you need to transmit at a certain slot. So let's say P is your probability that you are going to need to transmit in a certain slot. Okay, so you've picked your slot, and now what you want to know is, since my probability told me I'm picking this slot, what are the odds that somebody else is going to pick the same one? Well, if there's one other user on the network, their probability is 1 minus P. And if there's somebody else, their probability that they won't transmit this frame is 1 minus P. Because if P is the probability that you will, then 1 minus P is the probability that you won't. And if there's N total users on this network, then you're going to have N minus 1 of these that have to happen. So it's P times 1 minus P to the N minus 1. And so you can calculate that for given values and figure out what it's going to take to get something to do it. And the probability that any node has success is you multiply this out by all the number of nodes that you've got. So that's basically the way that math works. They made an innovation. They made it unslotted Aloha. They just let anybody send whenever they wanted. There was no more synchronization done. And that was much easier. People could just send things even if they couldn't hear, even if they couldn't hear the clock. They were too far away to maybe get a nice strong signal on that. They could at least try to listen and send. And that turns out to be even less efficient, but it was much, much easier. All right, so why did this network make such a huge impact like I'm claiming? It was extremely important because it taught us a way to do things inexpensively. Yes, it was brutal. Yes, you had lots of collisions. Yes, your network lost tons of efficiency, but it was cheap. And in the era that this happened, a guy named Bob Metcalf at Xerox's Palo Alto Research Center had noticed that every time they bought a device, a printer, a computer, or whatever, they had to buy electronics from the manufacturer of their LAN to hook that device up to the network. And the way it worked is they had this very expensive thing. In the IBM terminology, it was called a cluster controller, and you had to buy an IBM compatible card, which was expensive because you had to license the technology from IBM to be able to manufacture it. So part of what you paid, this third party, was a license fee that went to IBM. It's the reason why they're big. And this was expensive. So he set about trying to come up with some way to just kind of blast through all of it. And he had this idea of a type of network that would detect collisions and recover from them. So this is an analog, kind of a parallel to what we talked about with Paul Barron, excuse me, with Paul Barron's and Larry Kleinrock's papers, and work on trying to come up with a different communication scheme for the wide area network where every packet would have an address so that it could go out on its own without having to pass through a central controller. So let's take a look at a couple of examples of ways we graph this out before they actually show a slide with Bob Metcalf's name on it. So with this type of network, you're going to listen to see if the network is there, and if what you hear is just the carrier, which would be okay, it means it's idle, or if you hear something else. It doesn't matter why it's something else. If it's significantly different from the carrier, you're going to assume the channel is busy, maybe by another user on your network, you hope, maybe by some outside interference, if it's a wireless network or cable that's outside. Doesn't matter, you'll lay off. When it's available, when you sense that it's open, you will begin using the network. And you'll immediately start to transmit your frame. You'll transmit the whole thing on to the wire at once, but you'll be listening to see if that's what's actually getting put on the wire, or if what's actually on the wire now is your signal pattern plus another one that's arrived from someone else, in which case you're going to conclude there's a collision. So here at time t0, the second PC starts to send a signal. So the bits go in all directions allowed. This is a cable, so it's got two directions, left and right. And so as time goes on, the bits make their way across the wire. And they'll eventually make it to here and to here. And if we continue on, they'll make it to here. So this takes a little bit of time. This takes a little more time. It's going to take even a little more time before it reaches T1. So there's another way to draw this diagram, and it's to draw it as a pyramid. And so that's what you see happening right here. And so what they're basically showing you is, as time goes down the page, my packets go left and right. And so what I'm graphing is the position the packet is against the time that it happened. And if I graph that, I'm going to end up with these pyramid-looking shapes. So I'm going to erase this because their pyramid is a lot flatter. So this guy followed the rules, right? He listened. The network wasn't busy. He put his thing out there on the wire. This fourth PC did the same thing. He did exactly the same thing. He listened for the wire. He did it at a later time. Why didn't he hear that PC number 2, PCB, whatever you want to call it here, why didn't he hear that the guy had transmitted? Was there a volcano between them? No. It's just that not enough time had passed, even at the speed that these signals travel on copper, close to the speed of light, it hadn't had a chance to reach him. So he was also following the rules, and he started to transmit a signal as well. They're basically just sine waves, sine patterns, sinusoidal patterns, and they combine. They don't really collide. It's more accurate to say they combine at this time here, whatever this time is. Maybe we can call it T2 or T sub C for combine. And from that point on, it's as if there had been a new computer here that was fed 2 input signals, one by B and one by D, and took the combination of those things and started transmitting it on the wire here. And so this new signal started transmitting back. So in the meantime, B is still transmitting. So he's still sending new bits. His first bit is over here. The one that he sent right after that is here. But he's still got bits left to send. And, you know, he's got a big stack, a big frame here. So it's going to take him a little while to send these things onto the wire. And propagation is fast enough that he might be, let's say, here. This might be the one that's moved its way down and it's ready to go out to the left and to the right when this corrupted signal, this combination, makes it back to him. And when it does, what happens is he notices on the wire, when he tries to transmit this signal on the wire at this point, that's not what he hears as he keeps his ear to the wire. Instead, he hears this signal plus these 2. So he knows there's a collision, but he doesn't find out until later. So you need him to keep listening long enough that he is still able to hear the collision. So there's actually rules about the minimum size an Ethernet frame can be that are geared specifically to ensure that your packet, your bit, has enough time to propagate from one end of the network. If you're the furthest away you can possibly be at one end of the wire, that your signal can have time to propagate all the way to the other end and have somebody else collide with you by sending a packet right before you got there and like, oh, God, I almost made it, and he started sending something. Wouldn't you know it? And then for that corrupted signal to make its way all the way back to the other end, and you're still listening. So for you to be listening for that amount of time, we can convert that. If you tell me how many bits a second you can transmit or how long your cable is and the propagation length, I can tell you how big that packet's going to have to be. Okay, so you eventually will recover from this. So it's carrier sense, multiple access. There's multiple people accessing the network, and we now have the ability to detect a collision. So it's a CSMA-CD network. You'll hear that acronym frequently, and it's Ethernet. Think of it as Ethernet. It is not Wi-Fi. Wi-Fi is a little different. We'll come to that in a minute. Okay, so collision detection, it's easy in wired LANs. It's really difficult in wireless LANs. Why is that the case? And here's why. When I was A and you were D, and I sent a signal towards you, and right before it made it to you, you sent a signal. This is supposed to be a box, not a letter. And you sent a signal as well. Even though I've traveled some distance, maybe 100 meters, 200 meters, 300 meters, 500 meters, whatever the maximum length is allowed of this cable, let's say it's the maximum length, and the standard absolutely publishes a maximum length. And even though signal strength decays with distance, it's a guided media. The wire preserves all of the energy that's still available and keeps it going down this very narrow channel, down the wires. Okay, so none of it really much propagates outside. There's a little bit that radiates. That's one of the reasons why the signal degrades. Also, there's some resistance in copper. Not very much, but it does attenuate or reduce the strength of the signal the longer you pass through it. But even with that, the relative strength of this signal, by the time this corrupted path makes its way back to you so that you need to detect it, if your signal strength was up here originally, the one that you're getting back is still maybe here. So if this guy was sending this and now it looks like this, half the speed, it's still enough for you to screw up your signal and for you to tell there's been a collision because it's guided media. What happens on Wi-Fi? With Wi-Fi, when you transmit something from a radio, let's say it's your iPhone, and the Wi-Fi hotspot is here in the classroom or outside maybe, something like that. And this is also true of cellular. It could be true for a cell tower as well. Your signal goes in all directions, and it looks like concentric circles. So it's bad enough that the antenna here is this wide. And so if you run this back, in fact, somebody showed me a trick, one of my lovely students. If you run this back to here, and that's the width of your antenna, and you say, look, it's bad enough that the proportion of energy in this diagram that is actually reaching this antenna from what I'm transmitting, most of it is going this direction, and this direction, and this direction. Whatever percentage of the circle this is, 0.1%, that's all that is going to reach it. Plus it's degrading with propagation. And here's the worst part of all. It's not concentric circles. It's spheres. It's bubbles. So you have to energize this entire sphere as it propagates its way out with enough energy that there's something left in this one little Band-Aid sized patch at this one spot on this giant sphere for the antenna in the Wi-Fi radio to receive your signal. It is so weak compared to what you sent that if somebody else started sending something at the same time as you, and they're trying to get to the Wi-Fi router as well, the part of that that makes its way to you is maybe 100,000th, 1 millionth, maybe worse, the signal strength of your signal. So if you try to listen to what's on the radio waves at the same time you're transmitting, it's exactly like trying to hear what somebody 2 blocks away is trying to tell you while someone is screaming in your ear. It's just too great of a difference between the two. And in this case, you're screaming in your own ear. You're yelling loud and then listening. That's what you do when you talk. You have volume, sound that comes out here, and you get feedback through your ears. If somebody is trying to whisper to you from the other side of the room while you're talking, you can't hear them because even if they're speaking at the same volume. So it's a really tough problem, and so it does not work in wireless networks. It does not work in Wi-Fi. So we cannot depend on collision detection. We have to do collision avoidance instead. So we talked about this, and there's some abort times in here as well. There's a decent simulator, I want to say. See if I can find it here really quickly. CSMA collision detection. Let's see if I can bring this up. Okay, and I haven't played with this one. I may have changed it, or I may just not remember it. So what I'm going to do is set the bus length, the frame size, and the transmission rate. Well, let's just leave it the way it is right now. And then click on a node to generate a packet. So here's a node. And then here's one. The channel's busy. And 19 microseconds have gone. So he's sending something across the wire. And this guy tries to send. It's busy for him as well. And maybe I can stop him by... There, it's finally finished. Now B can go, and he goes in both directions. So these are too big. So what I want to do is see if I can make the network a little bit bigger. So it's interesting because this thing is probably to scale. And let me try sending it here. This guy can send at the same time. This guy cannot. But they both detect a collision. Do you see? It says collisions. Now green can send. And if he's done, if I do this right, we can have them all collide with each other. This will finish up for me here. So green's got the network. Nobody else is going to send. I'm going to click on both of these other guys. So as soon as it's done, they're going to they're going to send it, and he's going to start sending something as well. They're all going to collide with each other. They figure it out at different times, and so they have a back off, and they're going to pick a random time before they start again. Okay, so that's one tool that's out there. There's another one. Let me see. He may not have it in this batch anymore. He doesn't. He has a wireless one, but I'm going to wait till we get to the cellular chapter for that one because it's really, really cool to take a look at. Okay, so let's talk about what happens with CS and ACD. If you detect a collision, what Ethernet does is it stops transmitting its normal signal. It sends something that's a jam, so it can be sure everybody knows it didn't go well. And it's going to wait a random amount of time between 0 seconds and some value of K, which is 512 bit times. So not very long, few microseconds maybe, and it'll pick a time in there and start transmitting. Now hopefully the other guy picks something different and he'll start sending, and on average you're going to have 256 bits worth of time to hear him before you start. That's the way the math will work out. If you have another collision, either with him or with somebody else, you're going to double and now pick something in this bigger range. If it happens again, you're going to double again to 4 times the size, then 8 times the size, and 16 times the size. So you're going to start spacing out. And yeah, you could still pick the least time every time randomly, but what's the odds of flipping heads every time 1,000 times in a row? And if it finally gets too big, you'll give up on the network and you'll report that the network's down. So you can calculate the efficiency of this with the number of nodes, with the time to propagate across the network divided by the time to transmit on the network, and you can come up with an efficiency here. So this gives you better performance than Aloha, which is kind of nice, and it's super cheap to build. Taking turns protocols work okay, but nobody can get the whole network for longer than their fair share of time slot. So you pass things around on networks like this, and a master will send something saying, do you have anything? Nope. Or in this case, he did. He sent it back. What about you? Do you have something? Yes, I do too. Another way of doing it is called token ring, where you pass this special bit pattern around, and when somebody sees it, they know that it means it's their turn to attach data to the end of it if there's not already data attached. So you have to wait your turn, nothing to send. It gets over here, there is something to send, and you continue on. Cable access networks have shared bandwidth as well. So usually for most apartment complexes, if you look at the cable modem box, the light's blinking even if you're not using your PC because you're sharing that with someone else. So they broadcast the data out for everybody, and then you've got some upstream channels where you try to pull this stuff together. So they have an interface standard that defines how they mitigate this. It's called DOCSIS, Data Over Cable Service Interface Specification. And what they do is frequency division multiplexing upstream and time division multiplexing downstream. So it's a way for everybody to get a little slot permanently going up, and then coming down, you just wait for the packets. Your packet will be here soon. It's other people's packets. You might get like every 10th packet could be yours. And so that works. That scheme works okay. So we've looked at these MAC protocols, different ways of doing it, what's used in Ethernet. With collision avoidance, what ends up happening on Wi-Fi is you actually send a very small packet to ask permission of the Wi-Fi hotspot. And yes, you send it whenever you see the network is empty. Somebody else could see it empty at the same time. They could also send a request, and you guys could still have a collision. But the packets are tiny, so the odds go down. Right? The odds of 2 buses hitting each other is greater than the odds of 2 BBs hitting each other, or 2 little light rays hitting each other. Right? So taking turns is used by Bluetooth, token ring, some of the personal area network technologies. Random access is used by lots of the inexpensive high-speed LAN-based networks, and then you always have this channel partitioning that you can use for other types of technologies. So we're going to have an interesting problem assigned, but we're going to wait till we get back to sort of chart out in detail one of these collision maps and see what happens. But we're going to wait until next time to talk more about that because we're at the end of this one, and I want to basically end and give you guys a couple of minutes back early because I ran a couple of late the one before. All right, talk to you tomorrow. See you guys. Bye-bye.